at Princeton the last 2 years. And he's going to tell us about random point sets in the plane, I think, mostly. Is that correct?
Also on the line.
On the line, too. You're better. More understandable.
So, first of all, I would like to thank Chris and you all for the opportunity to be here and present my results. So, so what I'm going to talk about is mostly what is there. So, on the title, so rigidity phenomena and random point sets, and I would try to make it to address it to sort of a very general audience. So, I try to explain everything as we go by, and please feel free to stop me and ask questions if something is not clear. So let me begin with the random point sets first. So because we are going to provide the key models which we are going to concentrate on. So our key models are random point sets, which are also known in the literature as random point fields or point processes. So basically, it is a random set of points in an ambient space. So a simple example would be you take your favorite piece of your favorite space and you equip with some measure, and you throw down, let's say, the square equipped with the Lebesgue measure, and you throwing points uniformly independent of each other. That would be a simple example of a random point set. So, so if you throw down points independent of each other and identically distributed, that is a fairly natural notion of randomness in probability theory, and we will refer to it as independent and identically distributed, or IID. So this terminology will come up later also. So this is a very natural and simple intuitive example of a point process or a random point set. A slightly more complicated but still very interesting example are the eigenvalues of a random matrix. So you design your favorite random matrix with your favorite time of randomness, and you take eigenvalues. They will form a random point set on the line or on the plane, according as your matrix was Hermitian or not, and it will you can look at it as a random point set, and that gives you a point process. Another example is the zeros of a random polynomial, and from the probability theory point of view, what is most interesting is to take the large n limit of these finite dimensional systems. So somehow you let the number of points go to infinity, and if your system was well designed at the finite level, then typically the infinite larger limit typically converges to give you a random point set of infinite size on your ambient space.
But in the original kind of question, you're having there's a fixed cardinality, you're choosing n points for some fixed capital N. Eventually you could ask questions about how it behaves at ways to infinity.
Well, actually, most point processes you can sort of picture or imagine that way. But probabilistically, the most interesting processes, probabilistically the most interesting questions arise in the limiting object which you obtain. So just like so, you can equivalently imagine a random point set to be a random variable taking values in the space of point configurations on your ambient space. And just like a real value random variable, which is nice enough, is characterized by its probability density function. Similarly, for a point process, the probability distribution is determined by the m-point correlation functions for various m's, which are basically the probability densities of having points at locations x1, x2, xn in your ambient space. So somehow you can get, if for a point process or a random point configuration, you know these correlation functions for all x1, x2, xm and all m, then you would then that characterizes the point process.
So are the points being independent just correspond to this distribution being a product of one-dimensional things? Or is that not quite the
Yes,
same thing?
yes, yes, yes. So, okay, so let me now introduce the main characters in this, which are going to play a key role in this talk. So, first of all is the simplest and most celebrated example in some sense of point processes. So, it is a Poisson point process, and here is a simulation of a Poisson point process on the plane. It is characterized by so it is somehow in some sense it is the analog of the uniform distribution in the world of point processes. So the Poisson process is characterized by statistical independence of the points in two disjoint domains. So if you had two domains D1 and D2, and either of them could be infinite, and if you look at the points of your process here and here, then the statistical behavior of the points here and the points here are independent of each other.
So the picture we're looking at, are those just independently chosen uniformly in the square, or is there something more sophisticated going on?
Pretty much. Actually, so you can obtain the Poisson process by taking these uniformly chosen points in a, so if you take these uniformly and independently chosen points in a square and you let n go to infinity under the appropriate scaling, it gives you the Poisson process of the right density. So to generate this picture, what you do is that you generate a Poisson random variable with the appropriate parameter. So this gives you a random integer, and you throw down independent points of that cardinality inside the square. So let me introduce the next two examples, or the next two models which we are going to talk about. So it is a generic eigenvalues. I will define it rigorously in a moment, but as the name suggests, it comes from random matrix theory. And we have the Gaussian zeros, and here also, as the name suggests, it comes from the theory of random polynomials. And of course, these two ensembles exhibit non-trivial spatial correlation. So this independence property is no longer there, but they are interesting to study. First of all, because they were introduced by physicists and they have some physical relevance of their own. But also, if you want to model something, some process in nature by a point process, then often the assumption of, often the hypothesis of statistical independence in disjoint domains is not a valid hypothesis. It is kind of belies the basic nature of the process, and in that case, it would be interesting to have sort of natural and non-trivial models of correlated point processes. And these two are two of the key natural examples of correlated point processes on the two dimensions.
So is this correlation observable in this picture somehow?
So let me let me spend a moment on that. So in the Poisson process, you can almost distinguish from the Gini-Gray eigenvalue of the Gaussian zeros almost by Arlen's function, and it is characterized by the lumps like this. And since the intensity is held fixed at some level, let's say one particle per unit area, to compensate for the lumps, you have these large frequency spaces. On the other hand, in these two strongly correlated models, the distribution of points is much more regular. So it almost looks as if the point process has been generated by, let's say, some lattice, taking a lattice and perturbing it in some regular way. So So, and this is caused by the correlation structure of these ensembles. So, first of all, let us try to see why there are no clumps like this here. So, both of these two ensembles, they exhibit spatial repulsion or mutual repulsion on a spatial level when two points get close to each other. So, at short range at least, both of these ensembles, they exhibit mutual repulsion. Consequently, it is very unlikely to have large clumps like this. So there is due to the repulsion, there is a tendency of the particles to move apart from each other. But the intensity of the process is being held fixed at some level. So the particles cannot move too far from each other and create a big vacant space. So they cannot move too close or too far. So consequently, you get a more regular pattern of the distribution of points. However, from the simulations, it also appears that at least at crude visual level, there is a lot of similarity between these two processes. So it would be interesting to investigate as to what extent. So both of them seem to exhibit some sort of rigid or lattice-like behavior, and it would be interesting if you could sort of state and prove some concrete theorems about how similar they are and how different they are from each other with respect to their rigid or lattice-like behavior, and that is going to occupy part of our talk. So, without further ado, let me define the Gaussian zero and the Juniper ensembles. So the Gaussian zero, so the Juniper ensemble or the Juniper eigenvalues, as we already noticed, they are coming from random matrices. So they are eigenvalues of IID Gaussian random matrices. So, so independent and identically distributed entries. Note that we do not have any symmetry assumption here. So the matrix is not a Hermitian matrix. So the eigenvalues are complex numbers. And the typical size of the largest eigenvalue or the norm of this matrix is of order square root n. So roughly all the eigenvalues are contained in a disk of size big O of square root n. So without any normalization, already we have one particle per unit area on the average, and or a constant number of particles per unit area on the average. And if you let n go to infinity in this setting, the distribution of these finite ensembles, they converge to a limiting point process in the limit as it goes to infinity. And this is this infinite size point process which you obtain by taking weak limits of these finite finite particle systems is the Juniper ensemble. So it is translation invariant, and it is in fact ergodic under the action of translations. So let me just describe what do we mean by translation invariance in this setting. So translation invariant means that if you look at the distribution, if you have two small balls in two locations, x1 and x2, then the statistical behavior of the points here and here doesn't matter, doesn't depend on whether we send our balls at x1 or at x2. So the statistical law in a local neighborhood does not depend on the location in which you are looking at. And these are also examples of determinantal point processes, which are of key importance in various statistical physics models. So let me just take a moment to briefly allude to what we mean by determinantal point processes.
So what is the meaning of ergodicity in this context?
So the group of translations or the group of rigid motions has a natural action on point configurations. You move everything by the same vector. So then it acts. On this measure. So this pushes forwards the Juniper measure
of part 2. The whole
yes, act under the action. So so as we already noticed in the first slide, for nice point processes at least, the behavior of the point process is captured or determined by the finite dimensional correlation functions, m-point correlation functions for all n. So a point process is determinantal if its in-point correlation functions rho sub n is given by determinantal formula of the following nature. So rho sub n, which is the probability density of having particles at locations x1, x2, and xn, is given by the determinant of a certain kernel k with respect to a certain background measure mu. So you can think of mu as the level measure and k as some nice kernel, let's say the sync kernel, which we will probably have the occasion to encounter later. And this was introduced by the physicist Junipre as a model for non-Hermitian matrix ensembles, and it was motivated by Wigner's Hermitian matrix models for random Hamiltonians. So this is the non-Hermitian counterpart. And it is considered as a model of interacting particle systems in dimension 2. So let me now move on to the Gaussian analytic functions. So Gaussian zero ensemble. So Gaussian zero ensemble, we naturally think of a random polynomial, or when we think of random zeros. So the random polynomial is this polynomial degree n at finite level. It has independent Gaussian coefficients, psi 0, psi 1 up to psi n, and it has the scaling of these coefficients by square root k factorial, to which I will come to in a moment. And so now, when you have the random polynomial, you can think of the zeros, and it is a random point set, and you take a limit of this random point set as it goes to infinity, and you get what we call the standard planar Gaussian zero ensemble. And this now at the polynomial level also you can take a limit and obtain a random power series, and the zeros of this random power series coincide with the zeros of this limit, as one should expect. So the Gaussian zero ensemble is also translation invariant in the same sense as the Junipre ensemble, and it is also inverted under that group of rigid functions. And just to add a remark about this particular scaling, so this turns out to be the unique way to scale the coefficients of a Gaussian power series if you want translation invariance to appear in the limit. So this is a result due to Colloquium and Michels' work. So this also was the Gaussian zero ensemble was also first taken up by physicists and later studied by mathematicians. So it arises in the study of quantum chaotic dynamics, and here I should mention the work of Eugene Bogomolny, Dorigash, and their authors. So let me now focus on the sort of the specific type of questions we are going to ask about in order to study rigidity phenomena.
So these last two models, the eigenvalues and the zeros of the random polynomials, is it clear that these are distinct? Is it possible these are the same processes, just given two different definitions, or is it clear they're different processes?
No, so that's a good question. So in point processes, like if you have ergodic point processes, then they are either basically the same or they are mutually singular, and they are not the same. So you can compute the 2-point correlation function.
Okay, so you can compute some invariance and it shows.
Yeah, they are definitely not the same.
Okay.
So the kind of question we are going to begin with is the following. So suppose we have one of these planar point processors, and you fix a bounded domain. Any bounded domain set on the plane will suffice. For clarity, you can think of this. And you fix you fix the environment outside the domain. So you obtain a realization of your point process, and you fix the locations of the points outside. So these are fixed and unknown to us. And conditioned on them, you look at the behavior of the points inside. So in a sense, it is a conditional distribution in the world of point process, spatially conditional distribution in the world of point process. And just for starters, what is the answer to this question for the Poisson point process? Well, for the Poisson point process, the interior and exterior of the disk are two disjoint domains. So the behavior of the statistical behavior of the points inside and outside are independent. So conditioning on the outside doesn't tell you anything about the inside. The inside is still an independent point Poisson process or the same. So, however, the other two models, the equilibrium and the eigenvalue and the Gaussian zero models, they are spatially correlated in a strong sense. So we do expect the statistical behavior of the points inside to depend non-trivially on the configuration outside. However, what would also be natural or plausible to expect is that because of the high degree of regularity which is built into the definitions of the systems, for example, if you look at the definition of the Gaussian zero process, the basic randomness comes from independent Gaussian variables. Or if you look at the equilibrium sum, the basic randomness comes from the independent Gaussian entries. So it would be plausible or reasonable to expect that although the conditional law of the point of the inside points given the outside points depends non-trivially on the outside points, still there would be a fair amount of regularity in the behavior of this conditional distribution. For instance, one might think one way to formalize the notion of regularity for the inside point process condition on the outside would be to demand that the, let's say, the various endpoint correlation functions have a continuous density with respect to level measures inside this domain. I mean, this function would probably depend on the outside point configuration, but still we hope to obtain some kind of regular behavior of intensities. However, what we find, and this is joint work with Perez, so what we find is a very different scenario. So in reality what happens is that for the Juniper ensemble, the configuration of points outside, they determine exactly how many points they are annexing. So in the following sense, suppose you give me, suppose you don't tell me anything about what is inside, and instead you reveal to me the configuration of points outside. Then on the basis of this outside point configuration, I can compute a non-negative integer which will equal the number of points inside with probability 1. So in other words, the intensity functions or the distribution, the conditional distribution of the inside points given the outside is highly singular. And we also show that this is the only deterministic constraint which is imposed on the inside points by the outside point configuration in the following rigorous mathematical sense. So basically we show that if you have, let's say, if the outside dictates to you that there has to be 7 points inside, then these 7 points could be in any general position inside this domain. And a way to formalize this is to say that so if you have 7 points inside, then you can think of these 7 points as a random vector in D to the 7, and this random vector has a positive density with respect to level measure on D to the 7. What about the Gaussian analytic function? In the Gaussian analytic function, we show that the points outside exactly determine the number of points inside, as in the random eigenvalue ensemble. And to give an answer to your question in a very roundabout way, they also determine exactly the sum of the ensemble of the points inside. So here there is a law of, if you think of the number, if you think of it as a particle system, there is a law of conservation of mass and a law of conservation of center of mass. And subject to these constraints, there is no further constraint. In the same sense, so now if there are 7 points inside and their sum is S, you can they live on the vector. If you think of them as a vector, as a random vector, it lives on D to the 7 intersected with the hyperplane who's with sum S. And on this hyperplane there is a natural notion of restriction of the level measure. That's a natural measure of the hyperplane. And the law of the random vector of the inside points and the outside has a positive density with respect to the restriction of the level measure here. So that's the rest of the slide. So any questions about this?
So it's not very rigid after all. Yeah.
Well, it depends. I mean, but the rigidity that is already there. For example, the fixation of the number of points, or the fixation of even the fixation of the number of points renders ineffective many arguments of statistical physics, which are used to study stochastic geometry questions on these point processes. So if you have time, I will come to one of those. Yes.
So in both the random matrices and the random polynomials, the randomness came by using normally distributed variables as coefficients or entries of the matrix.
Yes.
Is the Gaussian really important, or do you just flip a coin, use random plus and minus ones, or you use random between -1 and +1 uniformly? Does it really have to be Gaussian for this to work?
So, yeah, so we have not explored universality questions here. So, yeah, let's do not answer. So, okay, so we now know that so for the Ginebra of the Gaussian zero ensembles, there are rigid constraints, so there are conserved quantities. So the vector of inside points, it lives on a constraint submanifold. But on this submanifold, it has a density function with respect to the natural measure on the submanifold, which depends on the configuration of points outside. Now, it is natural to ask whether we can say something about this conditional density on the restricted surface. And there we can show that this conditional density, of course, it depends on the outside, but it is roughly speaking comparable to the square random density. So, in particular, so this is most interesting when two of the points are getting close to each other. So this square random density vanishes like the square of their distance, square of their mutual distance. So almost surely the conditional measure exhibits quadratic repulsion, which is true in the so quadratic repulsion between 2 points which are getting close to each other is true in the unconditioned scenario in these two ensembles. So this result shows that you also have it in the quadratic setting, in the conditioned setting, almost true. Okay, so let me now move on to something which is somewhat related to what you were saying. So we are not going to tinker with the Gaussian coefficients here, but what we are going to tinker is with the scaling, and that leads to interesting results. So, but before that, let me define what we mean by digit at level k. So for the Ginebra ensemble, we saw that the number of the inside points is determined by the outside. So what is the number? If the inside points are z1, z2, zn, then the number is the zeroth movement somehow. It's very complicated to write now. The sum is the first holomorphic. And similarly, you can define other holomorphic moments. And you can ask these to be conserved, and maybe subject to the constraints on these, the points inside should have free distribution. So this is what we mean by rigid at level k. So the points outside should, so a point process pi is said to be rigid at level k. The points outside determine the first k holomorphic moments, as in here. And conditioned, subject to these constraints, basically the inside points could be in any general position on the constraint submanifold with positive probability. So it's a natural generalization of the kind of rigidity behavior we see in the Gini-Brainerd option zeros. So Poisson is at level 0, no moments observed according to this definition. Gini-Brainerd is at level 1, Gaussian 0 is at level 2. And it is interesting to ask for natural point processes for levels k bigger than equal to 3.
So if I read the definition correctly, you can only be rigid for one level. You can't be rigid for like 3 and 4 because the second condition
Yes.
violates
Yes,
the first condition for a different level.
yes.
You've got a submanifold.
Yes. Exactly. So the constraint submanifold for a higher k is a subset of the constraint submanifold, is a submanifold of the constraint submanifold. So the k, there is a family of Gaussian analytic. So in k rigidity we show, and this is joint work with Monica Krishnapur, we show that there is a family of analytic functions with Gaussian coefficients, and it's a one-parameter family, such that the points outside the disk determine nothing more, determine the first k moments and nothing more. So it's the rigid at level k. And what is this family? It is the natural parameters family is what we are calling the alpha Gaussian analytic function, where you put instead of square root k factorial, you put k factorial to the alpha over 2. So in particular, alpha equal to 1 gives you back the original Gaussian analytic function, which was started by the physicists. And there is a natural way of obtaining this, which is as follows. The standard planar Gaussian analytic functions, which is when alpha is equal to 1, it is a Gaussian and a variable in the Bargman space with respect to the complex Gaussian measure. And these alpha Gaussian analytic functions are Gaussian and variables in the space of L2 analytic functions with respect to other measures. The density is roughly generalizing the Gaussian complex Gaussian density. With Krishnapur, we show that the alpha graph alpha graph 0 process is rigid at level k for k alpha lying in this interval. So there is a phase transition in the rigidity behavior at alpha equal to 1, 1/2, 1/3, 1/4. Alpha you jump in there.
And you mentioned earlier only when alpha is 1 you get a translation invariant system. So these are not translation invariant zero sets. Are they more clustered near the origin, or they become denser as you go out?
Yeah.
The second one, they can become more dense.
Yeah, it depends. So alpha is equal to 1 is the inflection point. So bigger than 1 is something, and lesser than 1 is something. And we had simulations of that, but I did not include it in the slides. Okay. So another interesting question to ask regarding rigidity phenomena is the following. So suppose you have in a determinantal point process. So let us remind ourselves what we mean by determinantal process in this setting. So basically, the in-point correlation functions are given by a determinant of a kernel function and times background measure. So all the correlation functions and hence the behavior of the point process is encoded somehow in this pair K. Hence, in principle, the rigidity behavior of a determinantal point process should be able to, or is the rigidity behavior of a determinantal point process is also encoded in this pair. But the question is whether one can prove simple enough criterion on this K mu, which is easy to check, and from there, using which we can deduce some conclusion about the rigidity behavior of the resulting determinantal process. And what we proved with Krishnapur is the following. So if a determinantal point process exhibits rigidity phenomena, then its kernel K, if you think of it as an integral operator acting on L2 mu, then it must be a projection operator.
You said projection or contraction?
No, contraction gives you general determinant process. But if it exhibits rigidity phenomena for all bounded open sets, then it must be it. it must be a projection. Sorry, I'm sorry, it is a right answer. So it exhibits rigidity phenomena only if its kernel is a projection. So contraction gives you a general determinantal process. Any determinantal process, the K must act on it as a contraction. But for rigidity, you must have K a projection.
So that's a typo in the theory.
Yeah, that's a typo. I'm sorry. That is okay. So the converse of this is not true in general, and it's an open question for determinantal processes in so there are some counter examples in the hyperbolic plane, for instance, where the converse is not true. But on Euclidean spaces, the answer to this question is not known. Whether as soon as you are a determinantal process with a projection kernel, you must have some kind of rigidity.
So rigidity phenomena of what of rigidity?
Well, no, but this is an abstract space. So this really makes sense on the complex plane. This is an abstract space. So this is just saying that if you are not a projection, so if you are a proper contraction, then there is going to be some domain in your space where the outside will, where condition, if you fix the outside, and then you are allowed to insert a little points before it. So,
what do these moment conditions look like in the Hilbert space?
and this is very complex analysis. So this is very complex plane. So, before going to a Hilbert, we might like to formulate it in on the line of the Euclidean space, for example.
No, I see, but I mean, then you said that this, for example, the Gaussian analytic functions gives you these two invariants. But now you have the Bergman kernel of the projection.
Mm-hmm.
So how do we see that preserving these things is linked to the Bergman kernel being a projection? I mean, it is a projection.
Yes. So depends on which Bergman kernel. So actually we have a result. I don't think it is a part of the slides, but just let me tell you further. So we have a result which is of the following nature. So with respect to any, with respect to the Bergman kernel for any, let's say radially symmetric measure gamma on the plane, you can define a determinantal point process, and it is going to be a projection kernel. So it is not. So in principle, it could have a rigidity behavior. So it is not ruled out by this theorem. Now, under various moment conditions, on moment growth conditions on the measure gamma, we have different kinds of rigidity behavior. So if gamma is something like compactly supported, more or less, then it has no rigidity behavior. So there is going to be a point, there is going to be a domain where you can insert or delete points freely. If gamma is, let's say, like the Gaussian, or with infinite support and some other bells and whistles, then it is going to have rigidity of order 1. And in determinantal processes, this is the maximum amount of rigidity that we have seen so far. And this doesn't rule out the possibility of obtaining determinantal processes with higher levels of rigidity, but we don't have an example, and I don't.
So this is like I mean, your theorem is saying something the opposite of this kind of example. It's saying
it is saying that if it is not a projection, then there is no hope of rigidity at all domains. Okay. So subsequent to our work, rigidity phenomena has attracted some interest. And Alexander Bufetov and his co-authors, they have recently established the rigidity of the number of points, so the first level of rigidity for Air Bessel and other processes on the real line. So for the GUE sine kernel process, I showed rigidity in one of my papers during my thesis. So this was known, but from the random matrix ensembles, you can have other interesting point processes which are not invariant, but like the airy, etc. And rigidity of number of points is true for these processes also. So let me now move on to some questions with the by the way, so how much time do I have?
To the top of the hour, I think.
15 more minutes.
15 minutes?
Okay.
Okay. So let me describe a question with stochastic geometric flavor, which has some relevance to this rigidity phenomena. So you put it, out of any point process on the complex plane, on the two-dimensional plane, we define a random graph as follows. So you put a disk of deterministic radius around each point, and 2 points are connected only if their disks intersect. So you get a random graph embedded in the plane like this, and you ask for percolation type questions, so whether this random graph has infinite connected components or not. And of course, this is a somehow monotonically increasing function of r of the connection radius. And for Poisson point process, it is known that there is a non-trivial critical radius. I mean, non-trivial meaning positive and finite, such that if the connection radius r is smaller than r critical, then there is no infinite cluster almost surely. And for r bigger than r critical, there is an infinite cluster almost surely. And the infinite cluster, when it exists, is unique. And the proofs use spatial independence of the Poisson process in a strong way. So what happens in correlated point processes? So let's see, as I mentioned a while ago, so due to the rigidity even at the first level, at the number of points, many arguments of statistical physics can become problematic. So let us just see how they prove the, let's say, the uniqueness of infinite cluster and how rigidity can create problems there. So how they prove the uniqueness of infinite clusters is the following. So in the Poisson point process, suppose there are 2 infinite clusters. We want to rule this out. So what you do is that you intersect it with a big disk. If you take the disk big enough, then this disk will intersect both the clusters with positive probability. Now, for the Poisson process, you keep the outside fixed, and with positive probability, you can introduce a lot more new points here. This will happen with low but positive probability. And if you introduce sufficiently many points, then these new points introduced will, with positive probability, create a bridge between the 2 infinite clusters and link them up. So this shows that if you have 2 infinite clusters with positive probability, then with positive probability you should also have 1 infinite cluster. But the Poisson process is an ergodic point process, so the number of infinite clusters being a translation invariant random variable is almost surely a constant. So you cannot have with positive probability 2 and with positive probability 1. So this is a famous Barton and Finn argument, but we immediately see that fixing the outside, if we are not allowed to introduce new points, then it is then it creates difficulties for this argument. So what we do instead is that we observe that if R is big, then in expectation on the average there is order of R square many points here, and to create a bridge you need order of R points. So what we do is that, so typically there are a lot more points here than is necessary to create a bridge. So we now use the second part of our theorem, which says that if you, as long as you fix the number of points inside, you can basically they could be in any general position with positive probability density, and we move these many extra points, we move them around with positive probability using the second part of our theorem, and build a bridge between these two with positive probability. So yeah, so this is somehow how one way how the rigidity phenomena can.
So the more levels of rigidity you have, the harder it is to make that kind of argument.
Well, I think if you still have finitely many, you can, right? I mean, as long as the number of, as long as this and this are, yeah, as long as this and this are of 2 different orders, as long as the exponent is different, you can always find enough points to beat it. So it will be problematic if these two are okay. So this keeping the outside fixed, the ability to introduce new points is called. It is used a lot in the statistical physics literature, and it's called the finite energy condition. And in rigid point processes, there is the finite energy condition is violated. So in joint work with Krishnapur and Perez, we show that for Gaussian zeros unique eigenvalues, we have both phase transition and uniqueness. And uniqueness involves understanding of rigidity and tolerance, as I mentioned. So let me now move on to some questions of sampling theory, which is slightly different. So in flavor. So for a discrete point set in a discrete subset of the real line, we can consider the space of exponential functions generated by this discrete point set. And we consider them as a subset of n2 minus pi. And since we are dealing with thinking of Hilbert spaces, we consider the span closure. And it's a class, and the question is when do these exponentials coming from your favorite point set span n2 minus pi? And this is a classical question in harmonic analysis, and it is said to be complete if equality holds, and it's called incomplete otherwise. And it has been studied by a lot of stalwarts, Levinson, Redheffer, Georgin, Van Leeuwen, to name a few. And the classical results are parameterized by an asymptotic density of lambda, and it is complete. So lambda, E lambda, span of lambda equals the full space if the density of the relevant asymptotic density, which is called the Determinantal density, is bigger than the critical density, and it is a proper subspace if it is subcritical. But at the critical density 1, it is a tricky situation. So let us take an example to see. So under this notion of asymptotic density, the integers have critical density 1. So Z is 1. Now Z is complete because it's an orthonormal basis, it's a Fourier basis. But somehow it's too good because now if you take one point, if you take the origin out of Z, it is no longer complete, it's incomplete. But under any notion of reasonable notion of asymptotic density, it is going to have density 1. But maybe all these difficulties are arising at criticality because the counterexamples which we are considering is somehow they are too specialized. So because for example, if you think of Z, as a point configuration, it has a very kind of unique and peculiar geometry because every two successive points are equispaced. So maybe these counterexamples which are arising at criticality are by and large pathological, and maybe we should ask for a density completeness theorem by eliminating pathological point configuration by choosing a generic point configuration. And one natural way to make mathematically precise the notion of generic point configuration is to take an ergodic point process. But this was not known even for the Poisson point process on the real line at critical intensity. And this is, and for determinantal point process on arbitrary abstract space, you can define an analogous notion of completeness, and there is a completeness conjecture due to Lyons and Perez, which also appeared in ICN lecture of Lyons last year. So let me not describe that in detail, but let us just note that the Lyons-Perez determinantal sampling conjecture plus the after Fourier conjugation gives a positive answer to our density completeness question of the real line for the randometric sign kernel process. So this is the GUE sign kernel process at density 1. It comes from the eigenvalues of the GUE, and if you take local limits, you get this universal sign kernel process. It's a very natural point process in probability theory and in mathematical physics. And for this, and this is a determinantal process with the sign kernel. And for this process, the Lyons-Perez conjecture under Fourier conjugation gives a positive answer to the completeness question. And it also implies positive answer to analogous completeness questions in 2 dimensions, so the complex plane for the 4 quadrants. So
Sorry, could you say that last thing again?
So basically, you can formulate a similar density completeness question in the two-dimensional space.
So
Where instead of n2 minus pi pi, so instead of e to the I lambda x, your exponential will be this one. And instead of n2 minus pi pi, you consider the Fock-Parker space.
yeah, and then what you're saying is that if you take the kernels at some sequence of points, and
Yes,
it
which are coming from the Gini ensemble.
give you a basis.
No, there is a set of uniqueness. So the
That's
set
what I
of
mean. Okay. That's different.
These bases is different.
It's not true for a basis.
Yeah. But uniqueness and criticality is okay. So the we show that the Lyons-Peters conjecture for determinantal completeness is true for rigid determinantal processes. So rigid means and this is true in abstract generality. So you take your determinantal point process in abstract space, some metric space, you take any commutative domain, and the points outside to determine exactly how many points there are.
So what is the conjecture? I think it went by too quickly.
So I did not.
Oh,
So I am not
that's
focusing.
why I read it.
Yeah. So and consequently, after Fourier transform, if the Lyons-Peters conjecture for the sine kernel process, which is rigid, which you also showed in this paper, gives a positive answer to the exponential density completeness question for lambda sample from the sine kernel process, and also for the Fock-Parker space. So okay, but still the general question still remained open. And recently, with Timo's team, we show that for any ergodic point process of intensity 1, the exponentials almost surely span n2 minus pi pi. So this covers the case of the Poisson process, having unit intensity. It generalizes the result of the sine kernel process. And it also covers the case of a very simple point process, discrete one. So basically, you take the half integer lattice and you do perform percolation with recursive parameter half. So this gives you the half integer lattice has density 2. If you perform percolation with probability half, it gives you back a process of density 1. And for this, we can ask the density completeness question. And the density and the feature of this process is that the inner product of two exponentials has a very nice structure. So the Gram matrix has a very nice, sort of a simple random matrix. But even then, it is not clear how to use random matrix techniques to understand density completeness for this system. And this is also covered. This system is also covered by our result. So one object which naturally arises in this study is the Gram matrix of these random exponentials coming from the point process. And we study the asymptotics of the log determinants. So we are looking for Sego-type limit theorems. And what we show is that we establish universal Sego-type limit theorems for these objects. So maybe I will not get into the details of that because there is little time remaining. But let me skip also the Coulomb cases, and let me go on to something related to large deviations, because that is another aspect of point processes which I have been working on. So the key object of interest in the study of point processes is that there is a large polar radius R, which is basically saying that if you take a large disk of large radius R centered at the origin, then there are no points of your process inside this disk. So for various reasons, this is a quantity of key interest in point process theory, in particular how this decays to zero as R goes to infinity. And it is known that for Gaussian random polynomials of high degree, growing proportional to R square, the probability of this event is decays like e to the minus constant times R to the 4, and this constant is actually known. And what is not understood is the following question. Suppose there is a hole of radius R, so it's an unlikely event, but if we condition on that, how do the zeros look like? So the zeros will be now all outside. So how do they look like, even in expectation? So even the expected behavior of the zeros is not known, even the intensity is not known in expectation. So, okay. In the corresponding situation for random matrices is actually much better understood. So, for in one dimension and in two dimension, there is a particular kind of behavior which let me describe using this picture. So, this is the random matrix case. So, what happens is that, so this is the whole scale down. This is the outside points far away. So here far away is the equilibrium density of points. What happens is that there appears an accumulation of points at the edge of the hole. So this is the hole. There is an accumulation of points at the edge of the hole. So this, as r goes to infinity, it converges to a delta measure. And far away there is equilibrium distribution of points in expectation. What happens in random polynomials is our recent result with Elon-Ishii. So, and use large regression techniques to obtain this result. So, what we obtained is the result is the following. Let me just explain using this picture. So, this is the case for Gaussian and polynomials. So, what happens is that this is the hole. This is the delta measure of the spike which appears at the edge of the hole. So, this is very similar to the random Gaussian matrices case. But between the equilibrium intensity far beyond and the spike, there exists a forbidden region where the density of zeros vanishes as r goes to infinity. So this is a kind of a very counterintuitive and surprising phenomenon, and I will only say that we use large regression techniques to obtain this. Okay. And then we are in joint work with Shirai and others. We are using point processes to study various applied problems, real-life problems like distribution of sensor networks, and we are trying to use these correlated models of point processes to improve the various network parameters like the signal-to-noise ratio. And here are some simulations related to that, which show that. So the green is the Poisson, and the various the red is the Gini-Bray, and the various things in between are lattice perturbation models, which are approximations of the Gini-Bray. So the advantage of the lattice perturbation models is that they are not as so they exhibit they are less effective than the Gini-Bray network. But they are much easier to do simulation implementation. And how much time do I have? Okay, so on that note, let me skip the rest and thank you.
So you had mentioned that some of the point processes like the eigenvalues of random matrices arise in physics. I was wondering if the rigidity phenomenon that you've been studying, is that something that was predicted by the physics or anticipated, or are you just verifying something the physicists already claimed was true, or is this like a totally new thing?
I don't think so. I mean, I mentioned our results to Leibowitz, and he was very surprised.
I didn't know if it had any kind of physical interpretation of any sort.
Yeah, not that I'm aware of.
Okay, well, I had some other questions, but they're more technical, so maybe you just thank the speaker again.